Hello everyone, welcome you all to AIK Pathsala. In the last session, we had looked at the cases when we need to avoid recursion and when we need to use it. Now, in this lecture, we will look at how to write recursive method for any given problems in 3 steps. We learned from our previous lectures that a recursion function calls itself repeatedly until base condition is satisfied. A function calling itself is very dangerous as it is relatively less intuitive and may run into some runtime error if we don't treat it with extreme caution. So here I will introduce a 3-step approach that can make you confident enough to write your own bugless recursive function. So as an example, I will use a mathematical problem which is called factorial. In case you don't know what factorial is, let me just give you a brief explanation. Factorials were used to count permutations at least as early as the 12th century by Indian scholars. It's a product of all positive integers less than or equal to n. Factorial is denoted by small n and an exclamation mark. This notation was introduced by French mathematician Christian Cram in 1808. We can calculate factorial only for positive numbers. And the factorial of 0 is 1. As an example, if you want to calculate the factorial of 4, the answer will be like this. 4 multiplied by 3 multiplied by 2 multiplied by 1. So, how did we get this? 4, 3, 2 and 1. It's coming from the definition of factorial that it's a product of all positive integers less than or equal to n. So, in our case, n is 4. So, all positive integers equal to 4 and less than 4 are 4, 3, 2 and 1. So, the product of all these integers is a factorial of 4. Now, let's take another example. If you want to calculate the factorial of 10, so how do we do that? Again, we start from 10 and taking all positive integers that are less than and equal to 10. So we know that all positive integers that are less than and equal to 10 starts from 10, 9, 8, 7, 6, 5, 4, 3, 2 and 1. So if we multiply all these numbers, we are getting the factorial of 10, which is equal to this number. So based on these points over here and the examples that we provided here, we can express the factorial of n like this. This is the base equation for factorial. Now let's see how can we find out this factorial of any given value using a recursive method in 3 steps. So the step 1 is the recursive case, the flow. When we create a recursive function, the first thing that we have to do is we need to identify the recursive case. So we have identified that the general expression for factorial is like this. So how can we write the recursive function to have a factorial on both left and right sides of the equation? So if we look at this carefully, we can see that these parts over here can be expressed as n minus 1 factorial. If it is not clear, let's calculate the factorial of n minus 1 separately. So the factorial of n minus 1 is calculated like this. N minus 1 multiplied with n minus 1 minus 1, then multiplied with n minus 1 minus 2. Then it continues until we reach 1. If we do some calculation over here, we are getting the value over here like this. And you see that this expression over here is equal to this expression. So this means that we can change our function to something like this. N factorial is equal to n multiplied by n minus 1 factorial. In this case, we have successfully found a recursive case, which means that on both left and right side, we have factorial. Now we have identified the recursive case. Let's switch to Visual Studio Code to develop this case in Python. So here I have opened my Visual Studio Code. So first of all, I'm going to create one .py file here to write the code. So if you come here, you can see there's an option of creating a file. So if you just click on this and write the name of the file, I'm writing this file as recursion1.py. Fine. So this folder is created. Now after creating this folder, I'm going to write my factorial function over here. So let me write this factorial function, factorial, pass n as a parameter. Thereafter this function return n into multiply factorial n minus 1. N minus 1. Fine. Fine. So here I have created a function called factorial, which takes n as a parameter. Then it returns this expression over here, which is n multiplied with n minus 1 factorial. So this is our function for this expression over here. As you can see, we have just developed the recursive case in the Python. So our first step of identify the recursive case is done. In this code, you can see that our factorial calculation is almost done. You might be thinking that this function over here is enough for calculating factorial, but there is a bug in this code. So let's try to find out that bug. So here, first of all, I will call this function. So I will put factorial 3 here. So let me call this function for, let's say, factorial 3. So I'm putting 3 here. Now, to see what's going on, I will just add here print function, which will print n. So let's add print function over here, print n. Here also I'm going to add print. Fine. If we do not add print function over here, we will not see what's going on. So if I just save this code right now, and if I'm going to run this, let's see what will happen. Can you see? I'm getting an error that is maximum recursion depth exceeded. And it is printing till 995. So we see that Python raises error saying that maximum recursion depth exceeded while calling a Python object. This means that we have a limitation to keep number of units in stack memory. But it's possible to increase this stack memory. For example, to increase the stack memory, so here it was printing till 995. So to increase the stack memory, what I will do, we can import something like this. We can import sys sys, and then we can increase the stack memory. So let's do that. So I'm going to import here, import sys. Then I'm going to write here sys dot set recursion limit And let's say I am giving this 10,000 here. Fine. Thereafter, this function will come. So if I do like this, sys dot set recursion limit, in this case, you see that in the earlier case, what you are seeing this 9, it was printing till 995. But if here I am passing this 10,000 and let's save this, let's clear this here from here. Now let's run this function python recursion 1.py. Can you see what I am getting? Earlier I was getting 995. Now it was getting 9995 here. So it is printing till 9995. Thereafter, it is giving me this recursion error, maximum recursion depth exceeded. So what you have understood, we can increase the stack memory. But here our goal is not to increase the stack memory. Our goal is to prevent this situation. If you go back here, you will see that our function get called 10,000 times and never stopped. Because the recursion limit in Python is reached, that's why it stopped. So this means that there is a bug inside our function. So here we see that the function keeps calling itself without stopping. This will lead to a system crash if we implement it in an application. So the question is, how do we need to prevent this case? So to prevent this case and write bugless code, we need step 2. So let's see what is step 2. That is the base case, the stopping criteria. As you remember from previous lectures, we need a base case to prevent infinite loop. So here we need a base case for our recursion function as well, where it stops calling itself. So how can we do that? As you said in the definition of factorial, that factorial of 0 is 1. And it's obvious that the factorial of 1 is 1. So as a base case, we can use these conditions over here. Now let's switch to Visual Studio Code and see and make changes in our code. So I have returned to Visual Studio Code. So let's make some changes over here. Let's delete this part because I don't need it right now. Then let's also delete this thing. Fine. Let me write if n in 0, 1, then return 1, else return this thing. Then print this. Let's change it to, let's call this for 4. So here what I have done, as a base condition, I will write if condition. Over here, if n is 0, 1, then return 1, else return this thing. So if I, let's say, save this code and let's clear this from here. When I am running this code over here, you see that it calculates the factorial of 4, which is equal to 24. Fine. So if let's say, instead of this 4, if I will write something else, let's write 6 here. And let's save this code. And let's call this again. And see what I am getting this time. If I run it, I will get 720 here. Because the factorial of 6 will be 720. So you see that it calculates whatever value I am putting here, it is calculating the factorial of it. Now here, one more time, you might think that we are done with our code in step 2 because our code works the way we want. So why do we need a third step? So here I want you to just pause the video. Think if you can find what's missing in this code. Okay. And let's see what's missing over here. The most important thing to consider when writing a recursive function is making sure that the function stops for every possible argument. So here we need to identify in which case it doesn't stop. So for this case, we have step 3. So let's go back to our presentation. Step 3 is unintentional case, the constraint. We have base condition for our function, which is when n equals to 0 and when n equals to 1. And our recursive case calls the function itself with an argument of n minus 1. This means that the function will reach a base case only if factorial n starts with non-negative integer. So from our definition of factorial, we know that it is calculated only for positive numbers. So if we run our function for, let's say, minus 2 and 4.9, what will happen? Let's see. Let's rerun it and see what's happening. So if I put, let's say, minus 2 over here, if I put minus 2 over here and say this, and then if I rerun this, can you see? I'm getting an error. And what is my error? Maximum recursion depth exceeded. So you see that again we are getting the error that we got before, which is maximum recursion depth exceeded in comparison. This means that our function again is inside infinite loop. So we need to prevent this case as well. While there are different methods to achieve this, we'll use a simple assertion method in Python that throws an error if n is not a non-negative integer. So let me make few changes in our code to include that condition. So here write assert n greater than equal to 0 and int and equal to and this, then write the number must be positive integer only. The number must be positive integer only. Fine. Everything will remain same. Let's save this code and let's clear it here. Let's understand what I have written here. Basically, what we are doing here, before this if condition, I am writing this assert, which checks if n is greater than equal to 0. And the second case is n has to be integer. So n equals integer. Otherwise, it will raise an error. So the error will be like this. The number must be positive integer only. Basically, this line of code makes sure that n is a positive number and it's an integer. If not, it will throw an exception that the number must be positive integer only. In other words, we are forcing the argument n to be non-negative integer. So now our function is ready. So if we run the same case for this function with, let's say, something else, minus 2 here in this case, you will see that it gives another error saying that the number must be a positive integer only. So let's save this code and let's run this. Can you see? I'm getting this assertion error. The number must be positive integer only. Whatever I have written here as my error. This means that our function is not anymore inside infinite loop. So again, if you run this function for, let's say, some other value, some floating point value, 5.9, let's say, and save this and clear this, let's say, clear this and let's run this. Again, you will get the same error. The number must be positive integer only. So again, my function is not getting inside the infinite. Now, for example, if we run our function for, let's say, 10, then what will happen? Let's see. If I run it for 10, I am getting this output. Everything is fine here. So you see that it's calculated as the way that we calculate it. So with this, we have implemented last step successfully for our recursion function of factorial number. See you in the next session. Till then, keep learning, keep smiling.